Okay. Nick, close the door. Thank you. All right. So I guess Bert is not coming. Now we're getting to the point when I could literally see who is here or not. All right. First of all, thank you very much for sort of welcoming Bjarne. He is very grateful for what we did here, and he promises to send us rewritten or written. Well, the bird does exist. Ah. I already declared that you dropped out. So, he promised to send us the new concept proposal within the next 2 weeks. And he's usually good, especially in this case, since he needs to submit the proposal to the standard committee within, I forget, it's like 2 weeks also. It's very, very soon. He needs to convince his collaborators in all of that, but I think we did something good. So we will not talk about programming languages again. This is as much as programming language discussion as good for this course. So let us try to go back to what we were doing. If you remember what we did, we tried to work on merge sort, and we didn't do too badly. Let us, if Ryan will run .a.out, let us see what we have. So if I slightly rename things, the one which used to be known as Bert's sort is now known as 1/8. It gets 1/8 of the buffer. And we have 1/64. So let us see how it goes. And as we see, sort of, it's actually sort of shows us some good things. Even while we know that we didn't fix many things, it shows us that even when we go close to 1% of additional memory, 1/64 is between 1 and 2%, we are within, say, 20% of 20%, 30% of sort of having as much as we need, having half of the buffer, and we will see numbers will improve. So now, again, what we will do, we will continue the way, you will be sort of working on the code till we catch up. Remember, that's the catch up guy. This is the guy in the library. So we have to at least catch up with him. Would be nice to beat him. Is it possible to beat him? Yes, it is possible to beat him. How do I know? Before I started the course, I was able to beat him. So it's not, again, this is still my code in the sense it's just, but let us, we have a list of ideas. Let us look at the list of ideas. Sort of which one should we do now? Anybody remembers where we were? Should I? No, you guys don't remember anything?
I think we did 1 and 1A.
Yes, we did 1 and 1A, yes.
We did an adaptive merge.
But while we did an adaptive merge, what we didn't do is we didn't check whether we could improve on standard merge. Right? So we wrote adaptive merge, but we didn't improve on standard merge. We did not do rotate, but which one do you think will give us the highest payoff? Anybody wants to venture a guess? And easiest to do, and instructive. Yeah, I think insertion sort. Let us first go and look how we will use it. Because before before we even start working on it, let us look at how we have this guy where we could stick him. I think that you guys don't remember anything about the code? We wrote it together. Okay, it's merge.h. Okay, so let's ignore these guys for a while. Then let us go up, 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 up. We're looking for where we're going to use
Sort adaptive n.
sort adaptive n. So what would you suggest we do here?
If n is less than 16, then do something else.
Okay, I would not recommend saying 16. I mean, 16 is probably the right plausible number, but we either take a parameter or just say something like call it some name and then use define. So let us see who is going to write it. Ryan will write it. I think cutoff was a good. I don't think there is STD insertion sort. Should there be, by the way?
Very small ends.
And one should, by the way, let us stop here. This is an interesting point which we want to discuss. I wanted to discuss somewhat later, but it is an important point. When should one use insertion sort?
When copies are cheap and there's not expected to be a lot of them, and when data is already presumed to be partially sorted.
Could you be more specific, partially sorted?
There has to be about on the order of log n unsorted items in your container.
You're inserting a signal element into a sorted.
That would be a good thing. That would be good. But anybody could come up with a more general requirement. When it would make sense, when you sort of come and say, well, I should use insertion sort. I mean, let us by the way go step by step.
When the data fits into a cache line.
No, by the way, this is depends on how long the cache line. Let us remember where Hernan started. What did you say? When n is small. This is clearly one possible reason for using it. And again, how small? What is small? No, it actually doesn't. Again, remember, what is the number of comparisons, which is sort of something which determines the complexity of insertion sort? What's the number of the comparisons insertion sort is doing on the average? N squared over 4. That's what sort of a good starting point. Right? And what is the optimal we could get? The best. N log n. So when will this be approximately this? Well, we clearly could cancel that. So it comes where n is approximately 4 log n. Anybody could tell me what it is? This is a binary log. $16. Right? Is it exact? No, it's not exact. It's not, but it's a good rule of thumb that it's about 16. But is it the only case? Now we know. For example, if we have one element which is out of order, we need to insert one element. We do that. Or if we have, again, what is a good, how many elements do we want to insert using insertion sort? You have to use the same reasoning, guys. How many? Okay, so let us assume
16, somebody else mentioned that earlier.
no, we could do more. Log n is closer to that, yes. Right? But 16 is also, in many respects, remember that log n is not going to be that far removed from 16. Well, maybe by a factor of 2. Log n is a small number. Right? So what is this third case when we need to use insertion sort? This is the situation where lots of elements are out of order, but we still want to use insertion sort. What is the criteria?
If we know it's partitioned.
I mean, what sort of, you see, insertion sort is going to move an element from where it is to where it should be, one step at a time. So,
Well, when comparisons are much more.
no, you're going the wrong way.
But they're close to their real.
The average distance between
Where
Where it is and where it should
and where it should be is small.
is small, right? It's again nearly sorted, right? It's not sort. I mean, sort of. We shall see there are some considerations where you want to look at the relative cost, but they are not important for asymptotic assessment, right? Because a quadratic algorithm, whatever the ratio between move and comparison, still remains a quadratic algorithm. Right? So, three conditions. Now, after we talked about it, should it be in the library? Yes, it should be in the library. Is it in the library? No. Why? Because they threw it out. Okay, but it should be in the library. It should be in your personal library. Okay? It might not be called insertion sort. Again, the question is, should we call it as a library insertion sort when we put it in the library? Maybe not. Maybe we should call it. No, it's a sort. So what is a good name? This is not a bogus question. Finding a good name is important. Want to find a name which will somehow lead people to use it in these three conditions. Or sort almost sorted. Right? Sort of when things are almost sorted, either because there are few of them, or because only few of them are sort of out of order. Or it's just perturbed everywhere, but not by much. Then it's the one to use. And as we shall see, by the way, does it still have insertion sort inside? It has to, of course it does. So what happened during standardization process, they took something which wasn't the library and was used by the library and threw it out. The argument was, oh, we already have too many sorts. Okay? By the way, is it a good argument, too many sorts? No. You need to have as many sorts as people might need when they do practical things. assortment of them, yes. And they, of course, need to be sorted, you know, in some, right. But this is, how many sorts does it still have? Anybody knows? It does not have partial sort.
There's sort and there's Q sort.
It doesn't have Q sort. This is Unix, C Unix. Yes. So, what does it stand? Nobody, none of you ever used this term? Huh? So what kind of sorts does it have? Yes, it has stable one. That we know because we're measuring. Thank you. So we know it has stable sort. What other sorts does it have? Sort. Yes, it has. But you're cheating. You're yes. And anybody else has? Oh, yes, I actually do. It does have partial sort.
It has a heapify, doesn't it?
Yeah, this is heapify, it does, but the sorting algorithm is partial sort. When it sorts first thing, you want to find out first 1,000 out of 1,000,000. Something you frequently do around here. So what would you use? You would use partial sort, which will do that. Any other sort-related algorithms? Partition are kind of sorted related, but there's a very, very important one. No, it does not have merge sort. What is merge sort? Stable sort is merge sort. It has a thing called median, which is a nice, useful sort-like thing. What it does, it pins, for example, I want the 30 percentile element. It will pin this element at the 30 percentile position and put all the smaller before, all the larger after. So if I want them to find another one, I could pin, and then I could sort in between, and I could do many other things. It's sort of good to know these things, guys, if you intend to program. Now let us look how so. Insertion sort does exist. By the way, as insertion sort, let us talk a little bit algorithmically before we start writing it. How many algorithmic versions of insertion sorts are there? At least?
Two.
Okay, tell us.
Ordinary one and the kind of binary sort.
Yes. So what's sort of both insertion sort, the main idea is find where the element goes and insert it there, right? Could be used, as Bert says, could be done with two different ways. One, you use linear search of finding where it should go. Another one, use binary search, finding where it should go. And we'll explore the space. This is an interesting space. Are there any other versions anybody knows? There's a version which was invented by, as everything else, by Tony Hoare. He realized that one will look at the inner loop of insertion sort. You have to do sort of two things. You have to guard that you are not crossing by size, and then you need to guard that you're not crossing the first, right? Which makes the insertion sort do two comparisons per cycle. And there is an important thing which we will not do this time, but we will do it when we try to do the fastest sort possible. The idea is you could have an insertion sort with a guard. Assume that somebody puts, by some hook or by crook, makes the first element being the smallest. This is guaranteed. or somebody stuck the smallest element up front, then you could simplify the inner loop, just going through the algorithmic space. Okay? So let us call something. Which one will we start writing, by the way? Simple or binary? Anybody thinks, which one is simpler, do you think?
Simple makes sense if we're only using it for a small number of elements, because binary search has to do arithmetic and
But it will do much less comparisons.
much less is in less than 16.
Well, 16 is much bigger than 4. Log of 16. Okay, it's a tricky question, guys. It just so happens, I'm not supposed to tell you that, but I will, that with the equipment we have right now, it's easier to write binary insertion sort. Because we just done all the work which we have done, so we might as well start with that. Is it going to be really the best thing to do, or that we shall see? But it might be a good start because it's an important algorithm, so let us do it, since it's going to be very, very easy to do. Okay, so you called it sort almost sorted in. That's not bad. That's not bad choice. That's not bad choice. And then we will decide whether we use binary or, okay? So do we write binary? Let us create, I suggest that we create a file called insertion sort.h. Which const? For const, you don't. This is modern C++. Here's that. But, well, then, however, I would suggest you do not capitalize. The standard C convention, at least for old people, that all caps means it's a macro. No?
Often, if you capitalize all globals.
You would do that?
Yeah, they're visible from everywhere. The fact that it's a macro, I don't think it's that important than that it's visible from everywhere. It's a symbol that gets into every scope, and that's why.
Well, macro is not a symbol.
Well, yeah, but yeah.
Well, it's preprocessor symbol. It's a different.
Well,
What?
if it's a constant, it behaves as sort of.
Well, for sure you cannot undefine it.
And for our purposes, we're not using macros. So let's,
Okay. If we believe Bjarne, some of you might have read, if you didn't, you should consider reading his great book, Design and Evolution of C++. It's a short book and very, very instructive, because this is the book I hope he will revise, because it goes only up to like 92. In any case, the last chapter of the book is dedicated to the preprocessor. And it has an epigraph. Anybody remembers what the epigraph is? It says, CPP must be destroyed, and attributes it to Cato. Carthago delendum est. Carthage must be destroyed. So he sort of thinks that actually what he meant was CPP must be destroyed. So it's still not destroyed, but maybe one day. So insertion sort cutoff, 16, we will be changing it. And let us go and have a file called insertion sort.h. Okay, by the way, that's all right. Anybody remembers what was the requirement to now iterator in this sort where we called insertion sort? Yes, it required only forward iterator. So it would be terribly nice if we could come up with a version of insertion sort which would require only forward iterator. We'll see that it's actually a piece of cake as long as we do binary insertion sort. It probably needs to be some template or something. It probably needs to return. Yes. It has to be identical signature. Yes.
Sorted after. And just
Yes.
get rid of the buffer size.
And B. There's no B's. But it needs to return something. The same as the other guy. All right? Could we write it? Should be very easy to write it. I would say, well, no, I don't think so. What should we return? What do we return?
Oh, past the end.
Past the end. So we return.
Increment first, you return. Okay, so if n equals 0, however you want to write it.
That's how you would write it. Many people would. I knew a guy who would always complain when I would write this, line number 9. He's somehow not complaining now. See, he's complaining now. A way of avoiding it or hiding it under the rug, of course, to say if not n. But then it's sort of you're hiding it under the rug.
Yeah, no, go ahead with what you're writing.
You're going to deal with the one case.
Do you need last? Do you need to call it last? You could call it last, I guess, because it's going to be like, you could do that first. No, you don't need to use advanced. Plus plus is real good. I don't know. You guys assume that I know. I actually know, but I'm not going to tell you. That was our agreement. That we will be now, that I'll stop writing code. Okay, at least let me suggest something. Before you write, you have to come up with some idea of what you're going to be doing. Like, what do you plan to use?
I suggest that last points to the end of the sorted portion.
To the end or past the end?
Past the end of the sorted portion.
Sounds plausible.
Every iteration we do a binary search for what last points to inside the first class range.
And how do we terminate?
And then we decrement n, and
And why did he write line 12?
I think that can be probably incorporated into the loop.
By doing what first? By decrementing n. You could do that.
And return last after the loop.
And you probably will be incrementing last someplace. It's not going to stay the same for the duration of the algorithm, will it? Just yeah, what should you do inside the loop? So let us, do you write a picture?
We could do it right after the while.
Guys, do a picture. Always do a picture. So what you know, this is first, this is last here. This is last, which is sort of questionable last. We do not know where it belongs. And as Paramcha said, somehow inductively, we're sure that this is sorted. That's what you said, right? So, how do we know where this guy will go? Questionable guy. Yes. And here we're going just, do you use partition point? No. Thank you. What was this function called? Called upper bound. I think it was called upper bound. Yes. In some sense, here comes this thing that, knowing these functions, knowing them intimately would help. Why am I hesitating using upper bound? Anybody knows why I'm hesitating using upper bound? We implemented upper bound, guys, in the class. We talked for so long about it. Okay, could you show us the implementation of upper bound? Let us. Because you missed all the lectures and you don't know STL. In STL, straight binary search returns Boolean, for example. Learning is good. There is no straight binary search useful here. You could use this thing called grep. Upper bound, predicate, upper bound. Okay, so somebody tell me why I'm hesitating. It's all very simple. They're just one-line functions, all inlined, all reducing to simple things. But I'm hesitant to use upper bound. Why? I could let you do it, but then we'll have to rework so many things. And this is why not just knowing the interfaces, which is good, which would do much good if you learn STL interfaces, but knowing the implementation. For example, STL does not have this guy. Remember, they threw it out. And why is it bad that they threw it out? because to do this, we always need to do a distance. And for forward iterators, distance is expensive, linear. Right? So which one would be preferable if we could use?
You know what n is. So
Yes. So if we restructure our loop, that we actually know the length of this guy, it would be awfully good. You agree? Because then we could use what? Upper bound n, which is a non-standard function. Should be in the standard. In 15 years, or whenever people will learn, they'll put it back in the standard. Everybody? Right? So, and that, again, why maybe the idea of doing decrements here, going to 0, might not be the right way of doing things. What would be the right thing?
compare with n.
Compare with n, start a thing which goes up, which tells you how much is sorted. What's the length of this guy? Right? Let us not just do that. We will do that. We will do that. I'm sure we could. My advice that when you have n and n, the other one should be called m. That's what I learned in my elementary algebra courses. And if it's called A, the other one should be called B, never W. So, yeah. I would be all right. I would be good. I would be good. I agree. I buy it. He is right. Okay, so now we have some idea of what we could do there. So if we somehow, and we need to figure out sort of that all this is correct. So we got here, what do the first thing we need to do is to figure, by the way, why do we use upper bound, not lower bound? Right. If we use lower bound, what would happen? For equal guys, they will move all the way there. That would be wrong. That would be undesirable.
So insertion position equals lower bound. Or if you want to increment, I find with it. No, actually, I.
Last.
Why?
We need to get it incremented. We need to get, well, no, we got,
Oh, because once you put
so
it in,
now we
you
have one, at this point, we have one element. That is our element that is sorted already, right? And now we need to get the next element, which we're actually going to find the position for where it goes.
No, but maybe you shouldn't increment last yet.
Last is pointing to what we're going to look for.
Let us work on it. Yes, at some place, but before or after.
The start last is the element that we want to put in there.
No, but that wouldn't be right. You cannot dereference it before you check. I mean,
We checked already.
no, because you checked, let us assume, it's 0, then only first is dereferenceable.
Again, why is that not a for loop? Because we're defining a counter, we're checking for a counter, and we're going to be.
Well, we could write it as a for loop. We don't in this course. Again, because I hate for loops. You want to know why I hate for loops? Because the semantics of for loops changed about 6 times since I started programming in C++. You're too young to remember. Semantics of while loops never changed.
But for loops allow you to hide the counter in the scope of the
which is length. I would be a local variable.
When you teach the course, that's how you will teach it.
Okay, I submit.
Upper bound n.
No, we clearly have more than 0 elements. Since we checked, if it's 0, we returned. Yes. But let's not worry about it, guys. We will work on this after we see what we do in the loop. Because first we found, so now there is a tricky point.
And last has to be implemented before we call upper bound n. Because I mean we have to look for the second element.
No. Guys, don't worry. Inserting into an empty range is a perfectly legitimate thing. Whether we decide to optimize it or not, by sort of let us see what happens when you sort of do things. You came to this point, right? So you found an upper bound. Because that's where the difficulty is going to start. So what do?
We have to loop from insertion point to the end and shift everything.
And how are you going to shift it?
Copy current position, put the previous one there.
From the
And what's the problem there? Forward iterator is the problem. So how are we going to do it? There are multiple solutions, guys. By the way, let me tell you, if we have bidirectional iterator, there is a beautiful STL algorithm which would do exactly what we need. No. You should learn it one day. There are books about it. There is no shift algorithm in STL. You never even looked at it? Not once? So far, not a single function. You suggested binary search, you suggested shift. Who interviewed you? Oh, I interviewed you. I should have asked coding questions. Nobody knows in STL. See, I should have interviewed them too. Lucky you. So how could we, assuming that we have bidirectional iterators, to create a whole? It's an expensive way of creating a whole. And if we could use rotate, we don't need bidirectional iterator.
Oh, the whole is the problem? Swap.
No. Knowing algorithms is the problem. How do you create, if you want to shift things from here to there, how do you do it? But copy would not do the right thing. Why not? Because copy starts from the beginning, right? Therefore, it will just beautifully write this element everywhere. And it's a nice way. You could use copy for zapping bunch of storage. You put 0 in the first guy and then do copy, right? But it's not what you want, I hope. Rotate will work, but there is cheaper way. For bidirectional iterator, there is a correct way of doing it. If you cannot, no, you don't want to reverse. I mean, you don't want to change the order. No, I don't want to copy in the reverse order. I want to copy, for example, these elements are 1, 3, 7, 9. I want to copy them. 1, 3, 7, 9. Do you agree? Like that. Yes. That is, we need to do copy from the back. And there is an STL algorithm just for doing it. It's just knowing useful algorithms takes time. What is it called? Copy underscore backward. All right. So, but of course, before you do that, what do you need to do? You need to lift this guy, do copy backward, and do this. That's what you do.
But we don't have a bidirectional trade.
You might. You might. There is a technique which allows you to do what is the technique? We studied it. Yes. Moving things, creating a hole here when you have a forward iterator is more expensive. However, there are multiple ways we could do it. We'll do it. We will cheat. We will use, of course, Bert's suggestion.
Yeah, we just said go forward first and then we assign. So why are we? I don't understand why.
What?
Why don't we just take the step forward, then assign, and so on?
What do you mean step forward and design?
I mean, you read 3, and then you put 1 in its place. Then you read 7, you put 3 in the next place, right? You just need to keep 1 in a local variable.
Yes. How many assignments do you do? 2n. 2n. How many assignments will you do if you do copy backwards? What's the difference? Factor of 2. Right? It's not necessarily significant. You might not care about factor of 2, but it is factor of 2. Right? Yes. What? We should be, but our compilers here don't do STD moves. Okay. We shouldn't be doing STD moves. You will. When you teach the course, you will do STD moves. Okay? So you just invented, by the way, a very nice algorithm which we could implement. Right? Sort of doing this sort of.
If you have a 2 forward iterator where seeks are expensive and copies are cheap, then that's what.
Yes. We either want that or we want to do, well, since that one isn't the standard, and copy backward cannot always be done like that. You see, here we will be depending on the fact that we're shifting in place. Copy backward sometimes is used when the result and when the source and result do not intersect at all, so that you couldn't quite do that. It's not specialization. So we need to find a specialization of a new algorithm, right? And with Gaspar's suggestion, we just might call it shift, right? And then we specialize shift. We eventually might even have shift with some integral argument by how much, yes?
Is there a scenario where copy backward makes sense where the source and destination don't overlap?
Often. People use it in all kind of bizarre situations when, for example, they write copy backwards could take the output argument as output iterator. And then copy backwards would do reverse copy for you, if you see what I did. Right? So yes, they all, right? But
Makes sense to use. I mean, this algorithm makes no sense unless you have a random access iterator.
insertion sort?
If you had a linked list, you wouldn't be copying. You would just create a node and put it in the right place.
That's what you guys think. But maybe we will do some measurements. We implemented optimal linked list sort. Let us see. We cannot see it right now, but I actually think that, whenever we have time, we need to compare whether it's really faster to sort lists with list sort. Why do you think I say that, by the way? No, but why? I mean, ignore that. Ignore that. This is true answer. But why could it be a major issue to sort lists using optimal list sort, or what is known as optimal list?
You want to preserve locality.
List sort destroys locality of reference. And if at every CUDA, at every next, you get to a different cache line, then it's optimality. Remember what it does? It relinks them. So eventually, you get to a point where everything is literally sort of scattered all over memory. So when our lists are big, it's very often better to use this and to use ordinary merge sort, not linked sort, right? So we'll get, so there are multiple things. I mean, first thing is, let us try, we have things which work for forward iterators. Let us not drop this requirement. STL actually does drop this. Sort of STL sort, whether, all of the version of sort require random access iterator. And the reasoning behind was more, this was not the standard committee. That was me, but I'm not sure whether I personally agree with myself, even till today. Because the reasoning went like so. That most people, of course, don't know anything. Therefore, if you give them things which sort forward iterators, they will attempt to sort or do whatever operations, like non-linear operations on things like linked lists. These things are so much slower that the customers would be so much better off if they copy their stuff into a vector, sort stuff there, and then copy back. So I was a nanny. I was making decisions by saying, well, I know how to do it in the more general case, but I will not let them do it because they're immature. And this nanny control is not necessarily a good thing. So I am of two minds. Here I'm talking to you. Basically, I'm trying to not be a nanny. I'm going to say, look, guys, these are the spectrum. Sometimes you have to sort linked lists as linked lists because you have no extra memory. Does it happen often? No, it probably will never happen in your lifetime. But it might, just might, for one of you. Therefore, I want to show the full spectrum of the thing. This is why, again, I'm trying to sort of, there is something, STL used to have a sentence, I think I told you the story, which the standard committee threw out mistakenly. It used to, in the beginning of container section, it used to have a sentence that there are all these containers, blah, 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 but use a vector, right? This is a true statement. I mean, unless you are absolutely positive that you need something else. and you really spend days thinking about it. Use a vector. Vector is the most optimal. I mean, or using a C array is fine too. But, that they threw out. And there, for example, one of the lead lights, what's his name, Herb Sutter, was recommending to the world that they should always use DEC. I'm not making it up. I'm not making it up. He did recommend because he thought that, well, it supports more operation or whatever, you could do more things. He was wrong. Right? So I both wrote vector and DEC, so it's nothing. But DEC should not be used. And probably none of you actually. Anybody used? You used the DEC? Probably shouldn't have. Probably shouldn't have done that. It's again, I implemented it in few cases. It makes sense. So maybe in yours, but in general, it's a very, very sort of use a vector. So if I recommend use a vector, I didn't have to introduce any other iterators other than random access iterators. But I did. Why? Because people do use other data structures, right? So it's a yes, you're right in a sense. It should be random access, but we are trying to learn how to build these reusable components, and in order to make it fully reusable, you have to account for everyone, every potential use, if possible, without sacrificing performance. And I think we can. Right? It will require us writing, because we need to figure out how do we need to, okay. But first of all, we need to go with pizza. Do we eat pizza? Okay, let's go with pizza.